All right, let's get started on time. Welcome everybody to our SnapCon 2021 panel on creative ways to to assess or test Snap. Woo! Somehow it became creative ways to accept Snap. I'm accepting Snap. I'm officially accepting Snap as my savior. No. So my name is Dan Garcia. I'm teaching professor at UC Berkeley. With me are three wonderful TAs and support researchers with me. Irene Ortega, who unfortunately has strep, so we're letting her have a break for this one. Max Yao and Pham, and all of them have been critical to our all the hard work that you'll see in hopefully giving a sense of how we are moving forward to bringing different ways to assess Snap. All right, let's get right in. So here's the agenda for the talk. We've got an hour just to relax. We're probably going to go for 45 minutes and then have a chance to have some questions and answers at the end. The agenda is going to be Manifesto, some background. We're going to talk about question generators using PrairieLearn. We'll actually get into dig deeper into the actual questions we'll talk about. We'll discuss why this is a novel way of assessing materials, which is kind of neat. And then we're going to have a Q&A at the end, and feel free to ask any questions. All right. Manifesto. Many of you know this wonderful educator. Brian Harvey was my mentor, and as I was growing up for the last 30 years at Berkeley, I was able to lean on him for advice. And Brian had this wonderful perspective, which was that grades are evil. I think if you know Brian well, many things are labeled as evil, so you have to kind of take it with a grain of salt because so many things are evil. But in fact, Brian really captured for me what the sense was that what grades do is take the motivation away from just the pure joy of learning. And really, imagine having a outreach camp, right? Where you're supposed to share the joy of programming. Do you think you would ever add grades to that? No, people are there because they want to do it. So think about what would happen if you actually added grades to a fun experience. It'd be terrible. So that's just perspective. If we have to assess at all, we kind of acknowledge that the institution we work for is forcing us to do this, but if we had our own druthers, we would not have any grades. We would just have learning for learning's sake. And there would certainly be feedback opportunities for people, but there wouldn't be grades in the formal way. So just throwing that out there. Okay. Next, background. So here we go. Boop. So here's a simple example. This is +5. You can see what the block looks like. I am just showing this as an example of a function machine. Brian talks about a function machine that he mentioned. This is from Simply Scheme. And +5 is the simplest block I could think of. +5. By the way, my son has a second grade book that takes 3 as an input and has 8 as an output. It assumes you've got a nice reporter, +5. And what are the ways you can test a student's understanding of this? So here we go. The reasons behind the panel are, I went back into the archives to see what kinds of questions we used to write in our assessment. So this is UC Berkeley, right? This is one of the best public institutions in the entire world. And I looked at some of the questions we would ask on these intro programming exams. And I was part of some of this. I must admit that before I kind of woke up to different and unique and creative ways to assess early programming, I was doing this as well. So I'm not just pointing a finger because I was doing this as well. Here's what I found. Every single question on a midterm was one of two forms. It was either write +5, meaning here's a function specification, write it, okay? Or what would it report in the following case? Meaning, here's an expression, here's a function call, what does it do? That's it. That's all that was there on the entire exam. Write the code and trace it. That's all it did. Here we go. Don't believe me? Ready for this? This is actually the screenshot from the actual exam I dug up. Question 1, what's the value of the following expressions? Question 2, write a predicate procedure that, ... Question 3, write a procedure that, ... Question 4, write a procedure whose, ... Okay? Crazy. That's all they did. This is the way we used to assess programming, is just by saying, can you trace it and can you author it? There's got to be more creative ways to do that. So that's the motivation for this panel. I want to introduce you to Mike Clancy. Amazing instructor. He was one of the early teaching professors at UC Berkeley. He was here. He's retired now, but I want to just give honor to him. Because first I want to mention there's a meta point, which is there's not just one kind of teacher. There's not just one kind of engineer. Whatever career you have, if you look at someone who's successful, you don't have to just exactly model them. This is true in stand-up comedy. Don't just be Bill Cosby, Richard Pryor. Well, actually, don't be Bill Cosby at all. But don't be one of these great comics and just try to copy their style. Be your own person. So Mike hated lecturing. So I said, well, but he was amazing at content creation, amazing at making homeworks, amazing at scaffolding. So I learned so much from him. One of the meta points is that you can be good at some things and bad at some things, but be your own person. And there are many, many hats instructors wear. So find the things you're really good at and ace those, and struggle through the things that you're not so good at. The process of programming is messy, many ways to look at code. So be creative in the way you look at and assess that. Okay. Part 2. So in addition to the 2 that I showed before, which is just write +5 or write a function and trace it, here's what he came up with. Look at this. Look how creative he was. And he kept talking about, I literally over lunch, he kept giving me way after way after way of thinking about this, completely opened my mind up. Part of the purpose of this talk is to do the same thing for you. What's the domain and range of this function? So if I give you a function and some specs, can you describe what the inputs are and what the output should be as a result, giving some examples? How about what input causes this output? Rather than just, I give you the input, you trace the output, reverse it, flip it on its head and say, well, what's the input that might cause that output? That can be really complex, actually, if you have lots of complex code inside that takes different paths. Are there constraints on the input? Does it work for all lists or only lists that are non-negative values? Only lists that have numbers that are better than 5? What are the constraints on the input? How about this? Given the examples, write the spec for it. Or how would you rewrite foo, which is some larger function, if you had +5 as a helper? So here's foo here's foo written without the knowledge of +5, and somebody gives you +5 as a helper. What do you do? And what tests would you employ? Part of the question is, how would you make sure this thing really works? So that's another important thing as well. Okay. So far so good on that. All right, here we go. Next, in addition to these 6, we've given you a buggy +5. So Mike was really great about bringing in buggy +5s. So he would have a buggy piece of code. What would you do if you had a buggy piece of code? Well, what tests reveal that bug? Oh, look at that. What tests reveal the bug? That's just great. What should it have done? What did it do? What tests don't reveal the bug? Here, how about this? When I say what tests, I mean what class of tests. Not just here's a particular test, but actually can you generalize it to a class of tests that don't reveal the bug? And here's make a fix. And you try not to make bugs that are that many lines of changes. So what fix that we'd have, it's a one-line fix. His last point. What if you have a predicate? What if, it's a mystery? Rather than calling it +5, which kind of gives you the hint that it's supposed to add 5 to it, what if I give you mystery? It's a predicate. It's supposed to take some input, who knows what it is, and give you a true or false. What class of inputs cause it to return true correctly? Okay, remember, it's buggy. It's a buggy mystery. I didn't say that here. It's a buggy mystery. What class of inputs return true correctly? Don't trigger the bug, and which it's supposed to return true, and they do return true. Return false, and it's supposed to return false, and do return false. How about this? Yield a false positive. False positive is when it says it's true, but actually it isn't. And a false negative. It says it's false, but it actually isn't. Okay, so all of these cases. So let me give some background about a system we have been working with for the last couple of years. I presented this a year ago, but this is a very brief kind of summary of this and some updates, which is question generators using PrairieLearn. So first of all, let me put some context. What is computer-based testing? The idea of computer-based testing is this principle of question generators and randomization. And that means you're using question generators to generate a new question. Here I have, bottom right, I have 1 + 1. And the first question generator that comes with the system out of the box is, 5 + 3. And when you click new question, it says 2 + 7. And basically it spins up a random variable from, I think it was 2 to 9 or something, and another random variable from 2 to 9, adds them together. Now, sometimes you might want to be clever about that. Say, you know what, the kid doesn't know how to carry yet. So maybe 2 to 9 is the first number, or maybe 2 to 8 is the first number, and the second number is some number, but make sure whatever the number is, the range is so that it doesn't overlap. So if you say 8, it has to choose 1. So the point is you make sure it doesn't overlap. So you can put some constraints on how the random numbers are chosen. You can randomize the variables. You can randomize the orders of questions on exams. You can have a set of questions. Say these 5 questions are 5 different ways to assess, say, recursion, and I'm going to randomize among which questions a student particularly gets. Each of these are 5 independent questions, but I'm going to pick from that pool. I'm going to pick from a closed bag, a velvet bag, and then give the students one of those. And they can be auto-gradable, but they don't have to be. So you're not locked into writing questions that have to be auto-gradable. You also don't have to have any randomization. You can have a question that has no randomization, you're just using the system to deliver the data for you. It's better if you have randomization because then you can give it to different students and you don't have to worry about cheating, but it's okay if you don't have any randomization. So here are some of the elements that come built in with PrairieLearn. You have these standard selectors. So this is just like you've taken any online assessment. I'm sure you've done Khan Academy or that kind of thing. You have radio buttons, checkboxes, drop-downs. You also have fill in the blanks, and you can specify what those blanks should be. Are they numbers, integers, strings, data frames if you want to play with pandas. There are live editors. You can actually have live browsers in there, which is pretty cool. If you want to write an essay, you can do this. You have visualizations. You can display 2D, 3D visuals. You can work with external files. You can drag things around, lines of code. They have some Parsons problems there. There's vectors and 3D, really powerful 3D objects. So if you're teaching, CAD CAM, you can actually use this to teach CAD CAM, and they continue to add more elements as more people need them. And there's also workspaces you can bring into that as well. So prairielearn.org, open source, all of it's wonderful, all free. Please use open source software, good stuff. Here's what we're doing within BJC. Again, this is a talk of what BJC has been doing with creative questions. I haven't even got to this question yet. I'm going to get to that in a second. On the left, we're showing you how we write this in Snap. We usually put a picture of code. Snap is interesting that we have to now take pictures of a code rather than type them. And if you make different variants, you have to take all these pictures. It's a little slow. We've written some work. I haven't talked about that in this talk, but we do have some work to be able to generate Python, which generate a suite of XMLs. And I have another project that takes those suite of XML, a folder of XMLs, and generates a folder of the PNGs, the script pics of all the XMLs of the block. So it's pretty cool. So if I were doing all the same and I had a code generating different XMLs for what's in the report line, I could actually run that through our automated picture creation routine, and thanks to Lam and others who have helped with that, to be able to generate pictures automatically. So you got to script as much as possible. The tedium of making script pics is just really too slow. We also have this in Python, and this is not a very interesting question. This is, again, one of the bad questions, I would say, a non-interesting question. It's do this, predict what the output is. I just want to show you that we're playing with Python, we're playing in Snap, and we're trying to be as creative with Python as we are in Snap, and almost all the questions I'll show you today are Snap. We also have automatic feedback. So you put this in. This is like, what does this do? Again, this is not an interesting question. What does this do? If I call this, I give you a value of A, B, and C. What does it do? When you put in the number, it tells you whether it's right or wrong. And this is in homework mode. If you were in exam mode, it wouldn't tell you what your grade was. It would say, I've accepted your submission. But if you're in homework mode, it'll tell you got it right or wrong. And you can spin up a new version. This is a nice one. We have lots of different versions of this. And you can just keep practicing on it. So it's a really nice system to be able to practice in it and live in that space. And it gives you automatic feedback for how you're doing. We actually even have added tailored answer feedback, although obviously this has to be customized for each question, where you can encode what a hint is. So if they get it wrong, you can say, if they get it wrong in this particular way. It's not just a generic hint, it is a hint customized to the way they got it wrong. So they chose option C, and I'd say hint, when using map, the resulting list is the same length as the input list. So this is pretty cool that you can have a customized hint for each question if you do. Again, that takes more time to author, but it's lots of fun and really great for students. We also have, you might have seen this in the PrairieLearn picture, we have dead and live versions of Python. When I say live Python, it means here's a Python interpreter. You can type some stuff. You might even have an editor that you can play with, and you can say test this and play with it. That's called live Python. We also have dead Python. I call it dead in the sense that live Python gives you interactive results. We call it dead Python because it means it's not like a dead snake is floating around, but it means that it's just an editor. It's just basically a Python editor. It tells you your line numbers, plays with this, but you can't ever test it. So we call that dead Python, and we say that you cannot get the interactive element of it. So let's do it. Creative questions. Again, creative is a subjective term, but hopefully you'll find these questions creative. These are, again, very different than your grandparents' questions of write code and trace it. That's what we're trying to get away from, write code and trace it. What other ways can we assess Snap? Here is my example, and we're going to have now Max and Lam share some of this. But I'll start, and then we'll hand it off to the other folks to share. And by the way, I can keep driving the screen. You just tell me to change the slides if you want, Max and Lam. All right. Well, here's a snap block. Here's a snap expression. Item 1 of foo, pick random B to C. And we want to talk about the fact that we're in a functional world. A lot of times if you go to a Scratch class, it's all about commands, because Scratch really leans into commands. It leads into imperative or sequential programming paradigm. At BJC, we lean into a functional programming paradigm. So we care deeply about domain and range. Domain is the input a function takes. The range is the output a function takes. And we're now asking them, given this expression, you inherited some code from your neighbor. What's the domain and range of this, of foo and bar? So it's kind of a way of thinking about how does this play. You got some dongle. It's like how you have a dongle, and inside of the HDMI, and output is lightning. And so how does that work? Well, the input is supposed to be some video signal, HDMI, and output is lightning. We're supposed to send it to that. So it's how does this work with that? And here's the interesting thing. We make this a multiple, select multiple choice, otherwise known as checkboxes, to allow them to say, the domain could be very wide open, or the range could be wide open. So we try to give that more flexibility. How do I say it? More rope so someone can hang themselves by not having just a single radio button, but having having checkboxes. They have some sense of it's not just pick one of 4 and one of 5 or one of 6. It is I really have to think about this. And how we auto grade is there are 2 ways of auto grading radio buttons, checkboxes. You can either grade them. Each one is worth the same number of points, or so it's like separate. Treat them as 4s at the top one, the 4 separate true falses, or you can treat it as every time you're off, you lose a certain amount off of that. So you can grade them in different ways, and that's built into Prairie, which is quite nice. Second question, and we're hoping to get through. And by the way, we're going to have time to stop and talk, and even at the end, have you suggest your ways that you've been assessing Snap. I'd love to see those and have people share screens. So we'll take some time to make sure you understood each one of these questions. We don't have to rush this. We only have about 15 questions, and we still have a good amount of time. We're only 15 minutes into a 45-minute talk. All right, out of an hour talk, so we have 45 minutes left. So we have some time to sit and talk. Next one, Boolean Logic. We kind of ordered these in the order of how the semester works. So at the beginning of the semester, we're teaching about what functions are and what logic is. Students come to Snap and come to BGC as probably they're coming to you if you're an educator, without having programmed. It's rare to have someone teach a Snap course with a group of incoming students who have programmed before. So we're taking beginner programming students. They don't know what logic is. They don't know what if then else is. They also don't know what and or and not is. They're basically learning all of that for the first time. Now, sometimes you have some students who know it, but basically we're all bring people to the same page from Jump Street, from having no knowledge of that before. So this is an example of a piece of code, and I'm asking them to predict, if I tell you the output is true, what can you say for sure? This has a nice little logic puzzle to it, which is, there's lots of ways of looking at this. You can trace it, but this is different than a trace. Trace just, mechanically turn the crank and tell me what it is. If you're good at that, that's one thing. But here it's a different kind of beast. You have to understand what is almost the signature of mystery. You're kind of looking at what is mystery doing in terms of what its truth table is. And by the way, you don't have to solve with the truth table, although we recommend pulling up a truth table, understanding that is useful to do this. So you've got A and B as inputs, and what do you know for sure? I don't know whether A is true or B is true, but there's an option. Do I know A must be true? B must be true. There certainly must be false and must be false is an option. If you leave it unchecked, it means you don't know anything about it, actually. And none of these means I don't know either of any of them. If I only know about B must be true, but I don't know anything about A, then I would say just B must be true. And by not clicking the A, either A or C, you'll see that that's what it means. So it's a way of thinking about, can you predict what this is? Can you almost like reverse the truth table and figure out what you know about A and B to that, okay? So let's just walk through it together. Here's mystery. False, if it returns true. By the way, this is a nice one to randomize, because not only can you randomize, what we'll do as we're talking about this, each one will mention how easy this is to randomize, how many different variants of this we have. This is quite nice because you can have lots of A, B, truths, and you have kind of this if-else-y thing, okay? Maybe not a nested if-else. Maybe it's a simple if-else. And there's 3 slots there. There's an A and a B and a false. And there's the if slot, the report slot, and the other report slot. So if that's all you have, and you can put A, B, or true and false in there, that's 4 things you can put in 3 slots. It's quite a bit of combinations you can have with this. And that's times 2, because you can say, is the output returning true or returning false. Now you also have to make sure that you probably are using at least one A, at least one B, although sometimes you don't put a B in there at all. If you just have an A in there, there's no B, you know nothing about B because B is not even in the expression at all. it's probably good to have at least one of A or B in there. If you have nothing but there, you can't really say anything about that. And you have to make sure that you could return what you say. If you have something that's if true, return true, otherwise return true, you can't ever say if the output is false. Well, that thing is never returning false. So make sure that you can at least get to that. So not all the combinations are out there. You have to kind of think about that as you're making these randomized versions. So the only way to get this to get true, well, it can't be the else claim. It has to be that A has to be true and B has to be true. So this is like an and. You just think, let's think out loud. This is like A and B must be true. And so this is actually the correct answer. And now we're saying, can you replace the entire body? Can you rewrite mystery by thinking about and or and not? Now you're not allowed to use if. You only have this option. And we make this a little bit easier. This is on the earlier quiz. Make this a little bit easier for students because we give them multiple choice and you can kind of trial and error them. But this is basically the same question, and you knew that it was an and. It's only true when it's and A and B, and so the choice here is D, A and B. But and we often draw from, there's a lot of different combinations of options, and we'll often draw from a larger pool of them, making sure we at least pick the correct one, which is A and B, and the remaining 5, we call them distractors. The parlance for this is a distractor. We'll pick from a pool of questions to make it the distractor. So it's kind of cool. All right. Next. We're still talking about if-then-else logic. So we're still in the early stages of learning about logic. And look at this question. Goldilocks and the 3 numbers. You're given the following 2 helper blocks, min and max. You don't have to read them. It's just min takes the min of 2 numbers, max takes the max. By the way, that's now built into Snap. There's a secret. If you click the plus, if you drag the plus block into Snap and right-click to relabel, all of a sudden there's min and max. I didn't even know. It's like this hidden jewel. And most people don't know it, are rewriting it themselves, as we had to, but min and max are now built into Snap, but they're hidden behind a relabel. So you got to watch out for that. And we need to make that more public in terms of our Snap advocacy. All right, we're trying to write the median. So I've got 3 numbers, A, B, and C, and I don't know what's going to be big or small. I'm told that they're 3 different numbers. That saves a little bit. You can make this harder by making, I loosened it up. It could be that one of them is the same as another. Maybe they're all 3 the same. No, they're all 3 different. Let's make it easy. They're all 3 different, but they could come in any order. There's 6 different orders. That order is on the bottom. And, A, C is bigger than B, bigger than A, etc. Okay? And the question we're asking is, does this median work? But we're asking in a funny way. We're saying, here's a proposed median. We're not telling you it's buggy. It may always work, but it may not. So that's a powerful thing. We're not telling them it's a buggy program. We're just saying, here's median. And we're asking, under what of the following conditions does it correctly work? And that's really interesting. That's kind of saying, what's this class of things in which this median works? And one of the problems you can already see is that B and C get minned. So you find the smaller of B and C, and you pick the bigger of A. Okay? So if A was supposed to be the biggest thing, then that's going to work. That's going to be fine because whatever B and C do, they're the smaller 2 anyway. So when A is the biggest one, I don't care about B and C, the innermost expression of min is going to work, and A is going to be the max. So already I'm seeing that this is going to work if A happens to be the max, then that's going to work because it's the last thing I'm seeing is A is max. But I'm not sure this works. Maybe max and lambda. I haven't done this. I didn't have all the answers before ahead of me. I'm trying to do this live with you. I don't know if it works in any other cases. If B or C are max, you may not. Let's see. Remember, you want. Sorry, I was saying the wrong thing. I was thinking this is reporting the max. You want the median. You should be supposed to kick me. You're supposed to kick me under the table. Dan, we want the median, not the max of this thing. Nobody's kicking me. Say something, please. Raise your hand. I've done this before. I've taught the wrong lecture, and they say, Dan, weren't we supposed to teach yesterday's lecture? Oh, man. The whole lecture, but nobody told me. Okay, so please correct me. I'm supposed to do the median here. Okay, let's go back. By the way, can we edit this in post, Bob? Yep, okay, great. We can edit the video in post. All right, come back. And scene. Okay, we're doing the median here. When does this work? The median. Well, I know, okay, how about this? I'll go back to that. When A is the biggest one, that's not the median. Already I'm thinking, cross those off, right? Remember the argument I was making before? If A is the biggest, it's the median? That's wrong, because if A is the biggest, that's going to return A, the biggest. So A being the biggest, which is, I guess, the rightmost one, and the 4th one, cross those off. That can't be right. So you're thinking about when is this going to work. So this is kind of we don't have to go through the pedantically each of these options, but the point is it really makes students think about it and trace through and understand what's the set of cases when it actually would work. So that's kind of like asking this one, but in a way this asks for all the cases. When does it work? When does it not work? I'm asking that here with all the possible combinations. This was a fun question to author. And by the way, this has quite a few variants. You can, reorder which is min and max and play all around. There's a lot of different places you can reorder the median to have different variants for that. So we have some of that. All right, debugging. I love debugging questions. This is from Mike Clancy. I never had any debugging questions in my exams before Mike Clancy, and now I try to have a debugging question on every single exam. So I really strongly encourage educators on this call to think about debugging as a space. I love it. Here's this question. It says, you're trying to author a maybe possibly buggy, but I don't know. So I'm kind of like giving it on the edge. Is it buggy? Is it not? I don't know. Code because you want to return true when the number you are given has only ones. And this is that's the name of the question. We try to put jokes for our titles here. This is call 111, like call 911. So only one or 11 or 11111. Okay, so that's the idea. And it's at least 1 and false to otherwise. I mean, you can't have a number that's null. That doesn't make any sense. So it's a number, so it's at least one digit, and it's all 1. So basically it's 1 plus. If you think of regular expression, it's 1 plus. At least 1, and could be a lot of them. And false otherwise, okay? For each of the following 4 questions, what's the smallest counting? I love this question. This is hard. What's the smallest counting number that can achieve it? Remember, there's 4 cases. We talked about predicates, and we have these 4 options. I'm supposed to return true, but returns false. Well, that would be a false negative. Okay, supposed to return true, but it returns false. Supposed to return false, but returns true. Supposed to return false, does return false, supposed to be true, but returns true. And what's the smallest number that can achieve this? So they have to now, it's not just, can this happen, checkbox or not, but it's can you put a number in that actually does that? This really requires thinking deeply about this. This is literally just a for loop with a set and then a report, but it really requires them to think deeply about this. This is a really nice question to get to the sense of, do you understand kind of what the logic of what this is supposed to do is? Okay, so 4 different options. Play with this. And by the way, if you put a 0 if it's impossible. So we have a way for auto. And by the way, auto graded. Again, no TA involved. We put this together. Instantly, it's graded. Llama's like it's graded automatically. Like the exam closes at 12:01 p.m. We often give a 24-hour exam period at 12 p.m. 12:01 a.m. So 12:01 a.m. Bloop. Lam says, by the way, the midterm's all graded. Thank you so much, because we put in what the grade should be based on the randomness, and it just does it for you. So again, using these systems are great to do that for you. I'm now going to hand it over to Max, who was the author of this question, to talk about some of those questions. Thank you so much.
All right, thanks, Dan. Hey, everyone, my name is Max. I just graduated from Berkeley, and my advisor was Dan. All right, so let's take a look at the function composition. This question, we've been using it like every year for a very long time. And this was in fact one of the very first questions we wrote when we started, trying to use question generators essentially. And so let's check it out, right? So if you, from first glance, it's a relatively kind of simple question, right? And we do throw this question on, students all the time, during the semester. The question mainly kind of tests on the kind of understanding of order of evaluation, essentially, right? Basically, it just wants to make sure that students understand that, when you're evaluating, for example, functions, you can evaluate from the inside out, essentially, right? And we kind of play it into kind of constructing and just creating new ways of, mix matching these functions that are given to you to create something a little bit more powerful, right? Which is something that you kind of do in regular engineering practices. What we are trying, so when we were running this question, one of the, if you very look carefully into this, is that the evaluation we kind of have is always in the same direction, right? Sort of from left to right, essentially, right? So students who have, for example, have practiced a lot with this one, they might be able to kind of sort of understand the pattern, right, after a few tries. And we did have some discussions about, can we kind of have a different direction, right? Can we, instead of going from, let's say, left to right, can we do right to left, or mixed, right? We had some, discussions about it, and then there are, there could be some, we didn't really do it because there could be some ambiguity. But I think, if someone people in the audience, right? Like if you guys can think about ways to make it more like, mix or make it more interesting, I think this like questions like these could really kind of like sort of get students engaged in terms of just like creating like new things, right? And from what is given to you. This question also sort of ties into what we have, when we first started doing generators, is that we were thinking about different ways of kind of like almost sort of like categorizing, generators, so that it can help us keep track of what we have, but also sort of like expand the number of variants. What we say, it's very sort of loosely defined, but like kind of expand the number of variants we have that we can deliver to students so that they can practice on them, right? So if you look at this, right, Beethoven was a good composer, and then later on we had Vivaldi was a good composer. So one of the the question you see on the right is sort of kind of like a different way of delivering the question on the left, right, where you sort of like invert the question, and then you give them what you're trying to compose, right? And they ask them, what would you get with this, with this composition, right? So, besides the question, being like sort of like something we use a lot, there's also sort of like demonstration of ways to kind of like twist and turn the question to kind of, I guess, keep it interesting, but also sort of test students in a little bit different ways of thinking. Or anything you want to add then? All right. I think you're muted, by the way.
Sorry, no, perfect. You covered it really well. Yeah, perfect.
Let's go to the next one.
Yep, I'll go to the next one. Boop.
All right, cool. So this question is sort of, okay, so this is a more twist on the idea of composition, right? So the previous one, right, you're sort of kind of like given, what the, like what your goal is, right? And, and you're given like these intermediate steps on how that goal might be achieved. This one, we're sort of like twisted, like kind of like, sorry, okay, sort of completed very differently. We are given, all these kind of possibilities on, how to arrange, for example, these words and letters, right? And then we ask them, kind of almost kind of detach from, the traditional way of trying to trace, a program, but instead ask them to kind of like almost sort of like form a whole whole steps of thinking, right? A new way of like a completely different way of trying to approach a a question that's sort of like based on steps, right? So in this one, we're giving them, for example, swap flip, left, right. So these are sort of different ways to rearrange the letters, right? And then instead of asking them, what would you get, following these steps, right? Which we do have as part of this question. But what's more interesting about this question is that we ask them, how many different permutations can you create from a starting point, right? So in the example that we're showing right here, it's not very crazy. Right? There's only 3 letters. There are only 6 ways that you can possibly rearrange them, right? But so if you're a student, right, and you see this question for the first time, you really have to think about how might you besides understanding the fact that how the order of the functions are evaluated and what the results might be, but you also have to think about how to actually approach this question, right? You have to think at almost like a meta level, right? Where you not only have to understand what is the basics, what you see in the question, but you also have to think about how you might plan out your steps of thinking in order to arrive at a solution that you're confident with, or that let's say you might be able to prove that's correct, right? So we think this question is like really, really cool, right? It's something that you can imagine if you can probably just scale this as well, right? Right now with 3 letters, but some students, they might have, let's say they want to cheat and have a lot of time, right? They might be able to, kind of code this out very quickly, right? Because, soft left, right aren't that difficult to kind of code out. But you can imagine if we try to scale this up a little bit farther to like 4, 5, 6 letters even, right? Now, all of a sudden you have, this really, really like, it's almost like this takes too much time if you try to, let's say cheat, right? When you try to code on this out, you really have to like form an approach, right? You have to form a thinking process in order to approach this question, and then I guess be somewhat confident that your answer is correct. So I think this question is really cool, and I think this is sort of like we think it's a very creative way of sort of like twisting composing, questions and asking students, having them form a, very logical and then, well planned out thinking process.
And let me just add something, which is often these questions have like a low hanging fruit, then a higher hanging fruit, then a highest hanging fruit. What we're showing here is the hardest question. So this, what the question that Max lifted here is like the hardest question on the page. The first one is, can you just trace it? Very simple stuff. The second one is, what kind of input gives this output? So that's backwards, right? Can you run them backwards? So we talked about that earlier, but we're doing it here is actually quite interesting. You have to like almost invert each one of them and do it backwards on each one of them to make it work for the input. It's kind of interesting. And then we ask a question is, can you span the space with what we've given you? Which I think is a really different way of looking at these permutations. It's kind of fun. All right, on to the next one.
All right, cool. So this question is something that we thought was really, really cool. When we first, I guess when we kind of sort of starting to use the paradigm, right? There were a lot of capabilities that we're trying to sort of discover and also kind of show off, right? And there are many, if you have paper, right? If you're delivering exams on paper, you can do pretty much whatever you want, right? You can put diagrams in there. You can put, pretty much anything you just kind of anything you want, right? But when you're having like online exam, and then a lot of these we do auto grade. Right? This question is auto graded, right? So no one goes in and check the answers, right? This is completely done with a click of a button, right? So that's really nice. But also some kind of put some challenges, right? For example, the picture isn't the best, but so the kind of like the red little squares you see, they're basically checkboxes that students can click, right? Like basically if you think, oh, like the little the sprite is gonna visit that specific box, you just check that box right there. So on the exam, it's like it can almost like simulate your sort of like in-person like paper testing experience, right? Which you kind of would expect, but it's all done online, all graded, right? So that's really cool. So that's sort of kind of almost like demoing the capabilities of Paradigm, right? But again, this question was difficult to write because this was really stretching what Paradigm was, kind of designed for. There's a lot of kind of like little neat tricks we pulled in order to kind of to kind of make this possible. But hopefully Paradigm is gonna have like better support for this in the future. But kind of this kind of shows you, there's some really, really like creative and cool stuff if you just put your exam on Paradigm, like let's see, and this is saved a lot of time. And then this question was actually had variants, believe it or not, right? We have different scripts, like the meter script that you see kind of on the top, right? And if you actually kind of trace this out, there is a pattern to it. So basically, different students might actually receive different variants of this question, and they're all auto-graded, right? And imagine you're a student, right? And then you don't know what's how to, I guess, approach a question, right? It's sort of difficult to even like find another student and then try to, I guess, collaboratively, I guess, cheat on this question, right? Because students can have different variants, and then this question, if you don't get it, it's sort of difficult to try to collaborate on it. And let's see. Oh yeah. So I'm sorry. Okay. Yeah. And then what is it? Okay. So we're only showing like part A and B, right? And then we're also actually a part C. I don't think that's part of this the slides. But basically in part A and B, we're trying to get students to sort of like kind of slowly discover that pattern that they're kind of expected to kind of realize. And then part C, we're asking them to sort of like generalize based on that pattern, right? And then they would just kind of like select on this interface. And we think this is like, we really like these sort of questions where we ask them to like, I call them like kind of like robot questions, right? Where you not only like, because a lot of questions we see, on exams, they play with letters, they play with the lists, they play with the words, wherever, right? And numbers. It sort of kind of gets old, right? So like robot questions are kind of refreshing in a way, right? Where you sort of, you can like as soon as they especially for like I guess more introductory students, right? Is you can sort of see like code in action, right? You can sort of imagine, okay, this might be like a Roomba robot that we have, right? And then we're trying to program it so that because for Roombas, right, you really want to visit everything, right? So it really kind of puts your code into perspective, right? Just how freaking hard it is to try to program a robot to do what you want, right? But also in the process to kind of make it interesting, also enjoyable, and at the same time, you kind of sort of like think deeply about code and the effects of coding.
And I think there's another robot question that you helped with as well. Yeah.
Oh yeah.
Okay.
Yeah. Sorry. Is there a question in the chat? Oh yeah. So okay, I see the chat. So think that Matt, right? I hope that's right. So some students will tell you the question is like some students will say, oh, I had the same answer, my neighbor. How come I didn't get any points, right? So that's sort of I think Dan should come back to this question later because it does involves how we are delivering this exam. Especially during the pandemic and since we have moved to Perinar as well. So Dan's gonna talk more about for example student question stuff. All right, cool. So this question is sort of another kind of twist on the question I just showed you guys, right? Where you talk about robot visiting, but this one is sort of more it's sort of like the pattern, like not on steroids, but the students really have to understand sort of the code on almost like a theoretical level now, right? It's not simply just about finding a pattern that that's the result of the code, but also sort of strategically almost trying to like understand it, right? And then see what is going to happen, and then find pattern on top of that. So the kind of the demand for understanding is sort of kind of deeper with this question, because you can see on here, right? It's a maze now. It's no longer just sort of like I guess you can say like a plane or something, right? It's a maze that when based on the script that robot's moving, right? There are certain like corners, right? There's certain tiles that you simply won't hit, no matter how long you run it, right? And this is something that you sort of have kind of like based on I guess the movement, right, of the code and then and the spread itself, you sort of have to kind of be able to comprehend that the pattern of movement, right, and the implications of the the if else statements, right, that you have to kind of sort of generalize to like once you sort of have like one kind of like when you're trying to doing this question, or you sort of like start from like say one corner, right? And then you see, okay, so there's certain sides of this square or sides of this I guess turn, right, that it's not going to hit. And I try to sort of generalize to that all the other kind of regions within the map or within the maze, right? So this is something that's like really, really cool because it's almost impossible to even try to code this out and just work on your own, because this thing is meant to run forever, right? If you don't if the student doesn't understand this on a fundamental code level, it's they try to code this out on their own, they would just see it just kind of going around and around, and then they really have to kind of sort of almost pay attention to what's going on, or they might be very good at coding and then create something that kind of solves it, but at that point, what's the point, right? But so yeah, it's a very very cool question, and let's see, Dan, anything you want to add?
No, that's perfect. I mean, really, you could take the maze then and say, if I made the maze much bigger, you should be able to just get that. We didn't do that. This is kind of the biggest maze we had, but that's the idea. Can you kind of get the big picture and then be able to extrapolate to this? If you don't, this takes a long time to do pedantically, but if you kind of get it, you get the sense of that. So that's probably where we're coming from this.
We actually
the next one. Okay, great. Yeah, go ahead.
Yes, we actually do have a bigger one. I actually did that, but we didn't actually use it.
That's right. Yeah, we thought it was too big.
Yeah.
We thought it was
So
too big.
that kind of sort of like tells you guys the possibility of this thing, right? You can in the one we just showed you, we didn't really have we didn't really play the like variants on the maze itself. It's more on the script. Actually, we play on the the other way. So we play on the variants on the maze, not the script. But you can probably kind of sort of like play more variants on the script as well as the maze itself, right? To sort of like get like a lot of to create this a very wide number of different variants that students might be able to receive, and all have them all auto graded, right? So it's really, really cool stuff. Okay, now we can kind of move into higher order functions, right? This is something that this is the type of question we really like, in that we want them to kind of be able to kind of explore, and then different ways, where I guess not just different ways to kind of write higher order functions, right, to achieve the similar result, but also sort of be able to kind of like it ties a little bit into domain range as well, but also how things might actually kind of error out, right? In a setting where say students cannot they don't have like a live snap running, right? There's something that's kind of sort of like they sort of really have to understand what map keep well, Kamai's on in this one, but these fundamental health, what they do, right? What are the effects of them? What should you expect based on kind of the construction of these functions, right? And then being able to sort of like identify which ones would match up, right? So let's take a very quick one in this one, right? So looking at the first row, right? We have like the map R over keep items P from D, right? And then also keep item P from map R, right? For these two, they shouldn't be, they wouldn't, well, they're not gonna always yield the same results, right? Because on the right side, right, the keep item from map, after you have done the mapping, the list will be different, right? So now when you feed a different list into keep, you might end up with a different list now, right? Versus the other way where you kind of like filter the list first and then try to like map it. So it's sort of subtle. It can get subtle, right? But it's something that students should be able to recognize, right? And students really have to kind of like almost have to like be very careful, right? So I guess one might argue this might be a little bit tricky, but students do have to be careful about what is happening, with the side effects essentially, right, of map keep, et cetera, right? And then be able to kind of like trace it out logically and understand what is happening at each step of the way, in order to, I guess, make the right selections, right? So and this is also very generalized, right? We don't tell you, what RMP is, right? So you really have to understand. You really have to kind of like, I guess, understand map and keep on a more fundamental level and more generalized level, right? You can think of examples, but you really have to like you kind of have to see, oh yeah, what is actually going on, right? What do you expect running map and then running keep, or running keep and then map, right?
And the core of all this is domain and range. I'm looking at the clock and I'm making sure we keep on to get through all of these.
I'm sorry. Yeah. Okay. Yeah. I'm sorry.
The core. No, it's okay. The core element. I mean, you did a great job, Max, to describe it. But the core element we're testing here is domain and range, and you'll see there's a lot of the higher order functions. Let me show some other ones we've got. This is okay. Go ahead, Max. This is the other one.
Okay. Show. This is a hard question. This is a really, really hard question. And I even I get it wrong sometimes. But this is but it's something that we really like, because this one is kind of like the pinnacle of generalization and abstraction and assumptions, right? So you're given a sort of like a generic example, right? You have map something, you have keep something, right? You have combine something, right? We tell you it doesn't error, right? And then let's go on to the next slide. So being on top of this very, very generalized and very abstract assumptions, right? Now we ask you, okay, can we try to error it, right? So this is something. So like we have a lot of examples where we have is trying to ask you, can you make this work, right? Can you make that work, right? Kind of trace this out, right? Now we kind of twist it, I'm going to flip it, and then we say, okay, can you actually make this error, right? And this is actually sort of hard because you don't really have an example, right? It's completely generalized and it's completely abstract. So getting this right is actually kind of sort of like almost like twisting mind, right? You have to start thinking about trying to get something to not work all of a sudden, right? And then kind of understand, domain range is one way to approach this, but sort of like a different way of thinking about question. Let's go next slide. I'm sorry, I was going so slow right there. All right, cool. And then we asked them, can you work with specific cases now? Now that you have an abstract framework, right? So this one's a little bit tricky in that you cannot actually make everything work. But the thing is, now you're asking, the specifics, right? Now we have this understanding of what is happening, right? Now can you be more specific about, in your assumptions, right? And then try to make it kind of hack it to make it work, right? So this is kind of like a cool idea, right? You were bringing from like a completely generalized general example to sort of like specific but also generalized example. So something that's really cool. Okay, next slide. Okay, and now we arrive at possibly the hardest part of the question. And the previous two was already sort of mind bending. Now here it gets really hard. So we tell you so like a very small setup, right? Keep map keep, right? Setup is quite simple. And now we ask, okay, so what sort of conditions would actually make them work, regardless what MK whatever are, right? So this is so now we're building like so this gets progressively harder. So we have generalization, we have abstraction, abstract thinking, and now we're building theory on top, right? So you have to approach this from like a kind of like theoretical perspective on, how you might like what let's look at the second one check, right? So kx equals to knx for all x, right? You really have to like see, besides just generalize and thinking of abstract way, you can sort of like build a whole theory on top of what works and what doesn't work, and sort of like being able to kind of prove it in your own head that something like this, is what you would expect, right? And this is really hard. I did it myself just last night and actually got it wrong. But yeah, it's cool. It's a cool question.
That says that it may be too hard. I mean, we need to have some sanity checks in the room. It might be too hard if my star TA is getting it wrong. And we often use that to throw some questions out, but you're also maybe a little rusty, Max. So there's that. That's great. All right, I'm looking at the time. I want to make sure that we all get a chance to present. So Lam is going to take us home with the rest of the questions. Lam, thank you so much. And thank you, Max, for that. That was wonderful.
All right, thanks, Max. Thanks, Dan. Hi, everyone. My name is Lam. I did a lot of question generation in spring of 2021. I came to the scene after Max, so I took a lot of inspiration from him. He basically set up all the PL stuff, Prairie Learn stuff. So putting in new questions was very straightforward. And in college, I majored in CS and math. And in particular, in math, I really liked logic, mathematical logic, undecidability, incompleteness, that stuff. So I try to incorporate oftentimes logic into some of the questions that I write, logical deduction, things like that. And you'll see some examples later on. So some of these questions I authored, some that I would love to claim that I did, but the inspiration came from Dan and Max. So yeah, first one, this question is actually part 2. We omitted part 1 because it's one of those uninteresting questions that we mentioned in the previous slides. And in reality, as much as we want to only have interesting questions, sometimes we need to give out some free points. And the easier questions can be used to lead into the harder questions. So the first part of this question basically asks the student what the output will be for some mystery word and 10 for the second argument. This one takes it to another level where we're asking a student to provide the first input. By the way, we provided the second input being 0 to the script with some constraints, right? So a couple things to note about this question. Number one is that it's very easy or relatively easy to generate variants for this question. You see the numbers in blue. You can randomly generate those numbers. There's a certain pattern to it, of course, 4, 5, and 6. You can't have, as it turns out, you can't return something that is more than the number of letters you have. So like 5 A's and at least 4 B's, you can't have something like less than, actually I'm messing up, sorry. But the point is there's a pattern to that. I don't remember this very well. Second, a very important point is that, I wasn't going to finish.
I didn't realize you were not, sorry, I wasn't sure if you were done.
Yeah, it's fine. One additional thing is that we have additional constraints on the problem. So if you look at the prompt, it says shortest and at least 5 A's and at least 4 B's. So these are really interesting because it adds to the layer of the question. So not only does the student have to understand what the code does, they have to marry that understanding with the constraint that we give. So the question becomes like super hard, but doable. And there's actually many approaches to the question. You can either, sit down, understand the code, and then come up with a solution, or you can do a sort of guided trial and error. So you have the code here. You can try doing A 5 times and then B 4 times. It's not going to work, but you can look at the input and trace out the answer, right? And that's another way of approaching the problem. And this question is very nice because it also has that kind of flexibility. Okay, Dan, can you go to the next slide? All right, this one is one of those questions where the student has to understand the pattern. So if you look at the code, it's a recursive function that calls something, and the inputs we chose makes it so that it recurses 800 times. So it's actually impossible to brute force this on paper. So the student must realize the pattern and be able to generalize. In this case, the answer is 5, 4, 3, 2, 1. But to come to this understanding, the student has to like understand the code or try out some simple cases. So the question is more interactive and it requires more from the student than it appears. So yeah, good example. All right, this is one of the questions that I wish I authored, but I didn't because it's very nice. It shows that CS is really about problem solving, not about teaching a computer how to do stuff, as vague as it sounds. So in this question, it's actually a recursive problem in disguise. So on the right side, you see 2 examples path of that we can take to go from red to blue. And the constraint is that we can only move up and to the right or up and to the left, right? So the question asked, how many of these paths are there? And for this example, there are 28. And the way you would figure that out is actually by tracing, not quite tracing, but working backwards from the blue. So if you see the square from southeast of the blue square and southwest, you can annotate it with the number 1 because there's only one way to get to the goal, to the destination from those squares. And you can backtrack and fill out the rest until you get back to the red square. And by tallying all the numbers up, yeah, so it'll be 2 there, be 1 there, and then we don't have to fill all of it out. It's just that it's enough so that we get back to the red square. And in the end, you will see that there are 28, I think, 28 possible ways of possible paths to take. So you don't need the right side because it doesn't lead back to the red side, but yeah, that's how you would do it. So 19 plus 9 is 28. So there are 28 ways, 28 paths. Very nice question. All right, we can move on. All right, this is one of the questions that I authored that had that I try to inject in a little bit of logical deduction. So the scheme of the question is that you're given a list of Booleans. We try to choose the list so that the length is manageable. And we choose a function that is a truth function of 2 arguments. So think and, or. There are actually like 16 variants of it, but we don't show the student that. The student is supposed to figure out what L contains using only the inputs, or using only the outputs that are shown here, using map, keep, and combine. So yeah, can you go to the next slide, Dan? So given those inputs, you're supposed to figure out what is L and what is G, the predicate. I can go through the first couple steps. Could you go back to the previous slide, Dan?
We might not have time for that because we only have about 2 minutes left. I thought this was the most creative question I'd ever seen in terms of the levels of it. And actually, students commented how what Lam did to have a lot of steps to walk them through it convinced them that they could do this. When we first saw this, it was just, what is it? And you had to just, on your like a Sudoku puzzle, do it on your own. But then Lam added a lot more steps, like maybe 10 steps, I think you remember you added. Like, okay, what's the length? What does it have? And it really helping them one by one, like kind of walking them through how you'd solve a Sudoku, which I thought was very, very clever.
This question, but the nature of the exam, we only had like 5 points to spare on it, so it's very funny.
Yeah.
Like question had like 20.
No, next time we do it, we'll get more points. So this is such a rich question, and it had lots of variants. So one of the things we mentioned, we're going to reuse these questions. That's what's so nice about them. We're going to be reusing every semester. So I'm so delighted all the work we put into is not lost work. It's invested work that we can now pay back. You want to keep finishing us off for this last question?
Sure. Yeah. So you can tell that the length of L is 4 because map keeps the same length of the input list. So from that you can glean that the answer is 4, the length. And given that for this, you actually have to go back to the first slide for this question. Let me show the way we figure out what L contains. It's you have to realize that keep, and this is not shown to the student, they have to figure this out from their knowledge of keep and map. Keep basically does a map and then filters after, right? So whatever the content of L is, keep actually runs the function, runs map on it, and then it ends up with a bunch of true and falses, and it only keeps the true values, right? The values that evaluated to true. So you know that one of the items, the second one, since the output of math, if you remember, the second one is true, that item is actually kept. And keep, kind of like mirroring that correspondingly, keep actually keeps the location of that item, which is 2, and it returns that item. So you know that the second item has to be true. And for the rest of the list, if it's not true, that's a nice thing about Booleans. If it's not true, it's false. You can actually figure out the entirety of L. Given L, you can actually fill in the truth table now. Map, basically, it's fine. Everything is included in here. So if you don't have time, we can just end it here.
Okay. All right. I'm looking at 6 seconds left, folks. Thank you. Thanks to Max. Thanks to Lamb. Thanks to all the hard work that you put in. And Irene, we got to make sure we give her a lot of love. She put a lot of work into the system. Thanks for all that. We're at time. We're supposed to take a break. We'd be happy to have some questions if you want to. Sorry for running late. We actually tried to build in some questions, but I took a lot longer in the early parts of this, so I apologize for that. But thanks all for coming. Love to be able to answer any questions and talk about that. We're going to head off one of the questions, which we know is coming, which is, can you get access to the system? And that we know about that issue, and we want to try to make sure that we can give teachers access to our questions so that you can roll your own exams. We have to create a whole way to do that, because right now you have to copy email addresses, Max and Lamb know this, into a file, and it's there and it doesn't scale. We need to make a way to scale, but we really would be excited to and I can, if people want to see how to actually do this, I'll just shut up. But let me stop now, let people leave if they want to. But thank you so much, folks, for coming. Again, let's give your hands to Lax and Lamb for this. Is a wonderful panel. And I'll just show, if you want to stay for a while, I'll show you how we get into this system. So I go into login, and I log in through my authentication. I'll just show you fast. But thank you, folks, for coming. This has been great. You choose BJC. I can actually directly go to course instance. You have courses and then instances. So we're going to go to course instances, maybe Spring 21. We'll go in here, and here's all the assessments we have. I'll just go to the quest, which was one of the easier ones, and I can scroll down, and then you can play with, some of these things. So here's the HOFS question I think I showed earlier, which is saying, here's numbers. Oh, am I sure this thing? A non-empty list of numbers. What are all the possible return values? Okay, so here is this list. And you say, well, what goes into doing this? So I'm just showing a demo that Max or Lamb could easily have done. I click on Files, and I get 3 files. Info.json is the metadata that keeps track of the file and what it is and what the access is and what some of the, who authored it, all of that. Question HTML is just the HTML that renders this. All this is just the HTML that renders this. And here we have, we're even telling this that this is PL answer and the correct is false, and here's the true one here. So we are already just hard coding what's true and false. This is an easier one that doesn't have a lot of Python there, but there's also a server.py file that you have that can generate different pairs. So this is the one that's doing it. And if you notice how clever this is, we're actually generating different pictures. So by doing this, here I'm choosing number of same pairs is 2, number of different pairs is 11, and then those numbers factor in here. Once you're setting these variables, you can use the variables in any way. Choose different pairs is 5 minus number of same pairs, and then some of those things is, for I equals this, and your image 2 is this. So you're randomizing the images. And by the way, you can see what that looks like when you actually click on preview. I'll just make this smaller so you can see kind of what this looks like. Here's this. This has a lot. This has a map and some keep and a combine. And if I click on this, what this is going to do is maybe this one isn't, each one of these randomizes a different version of this. It might spin this differently. Let me actually get one that really does differ, every one that's just so different. Let me go back to this one. Here's some binary hex and decimal stuff. So here's this, same idea. Here's, base 16 plus base 2, and the answer is base 10. And if I click this again, look what you're getting. Now it's base 10 plus base 16 in base 2. So it's basically the triangle of base 2, 10, and 16, and out of 2 and into 1. That's what we're doing. And so as I'm clicking preview here, it's generating a ton of different ones. This is currently set to assessment mode, so you get one answer, but you can imagine flipping the bit and make this be in homework mode, and then you could do that. So let me just show you the files behind that. This is just general stuff. Here's I say, what is converted number 1, base 1, converted number 2, base 2, and then here is solution, base 3, and this is correct, and the rest of them are false. Okay, so let's remember this, that the solution is the right one, and the I0, I1, I2, because picking the distractors is key. So all these parameters, this is like a Mad Libs or a mail merge. All these are being filled in by the Python. So I go over here, and let's now see how we spin that up. And this, I think, Lamb, you authored this one. This is a really big question. This has a lot of details of how you're kind of doing the math of this. But essentially, you're just fitting this in so that every single time you're correct, all these hopefully are equally difficult, and all this code is just filling in those values. Here's the choices, here's the i's, and setting up the param. This is you setting up the params file for the I0 through I1. So all this feeds into the front end that you just test by clicking this. You just click preview, and you get different versions of this. Right now, we still don't have the way. There's a random. It's almost like testing a dice by throwing the dice. That's broken. You want to actually be able to say, well, can you make the dice roll a 1 and a 2 and a 3? We don't have that here. So we're building that as one of our projects, building that as a to-do to make sure I can click not just new variant, but next variant. So I can make sure to spin through all of those. Now, this question might have 1,000 variants. So then you want to think about how you're doing next variant. I certainly don't want to click this 1,000 times. You want to think about, Max has been a leader on this, thinking about deciding between structural variants and numerical variants. We call them conceptual variants and numeric variants. I don't need to test all the numbers, but I need to test the structure, right? So there's 6 different structures: hex, binary, and decimal, and there's 6 different ways that can be out of 2 and into 1. So I want to test each one of those 6. I certainly don't need to test each of the numbers within that. That's called a numerical variant. This is a great example to show the difference between a conceptual variant and a numerical variant. All right. I do want to make sure people get a break before our last session. We're done, by the way. I'm supposed to advertise what was supposed to happen. We're done with the day. Thank you so much for coming to SnapCon today. We are having an amazing social event in 10 minutes, so I want to make sure you get a chance to walk out and come back in. If you go to the link on the calendar, on the schedule, you'll see a link to go to, I believe it's Oye, and we're going to all experience a virtual SnapCon. It's supposed to be really fun, and it's we're going to be walk around. It's really fun. I don't want to leak it, but it's really fun. Please come back so we can get to meet each other. Thanks so much for coming to our talk, folks. That's been wonderful. Good stuff. Thank you.